Uh, okay. Recording. Okay. Thank you very much for invitation, and I'm very happy to meet many Russian mathematicians. And so let us start my talk, and thank you very much for invitation and introduction. And my talk today is about everything is overseen, and my talk today is rather elementary things. I apologize, and I'm my main program today I'd like to discuss is the following open-minded questions asked by Dini and Shimoni around 2005 when I met them in some conference. After that, I'm interested in this program. The program is just to find interesting. Today, I restrict smooth projective varieties with interesting automorphisms of positive entropy. I'd like to explain the notion of positive entropy soon after this page. And in this program, interesting is not mathematically defined notion, but in my talk, I'd like to explain one phenomena which I recently found. So very roughly saying that only existence of automorphism of positive entropy completely determined variety uniquely among some reasonable categories. And main theorem today I'd like to discuss is the following. So today I'd like to consider abelian fibered Calabi-Yau threefold. Here, Calabi-Yau threefold is smooth projective threefold of a complex number field with trivial canonical class, and underlying complex manifold is simply connected. So I don't need to explain this too much, but this is a very fundamental object in mathematics. And as I explain later, there are several cases Calabi-Yau threefold has fibration. And today I'd like to consider Calabi-Yau threefold with abelian fibration. This means general fiber is abelian surface. There are a lot of such abelian Calabi-Yau threefold, but if I assume that this abelian Calabi-Yau threefold has an automorphism preserving fibration, but with positive entropy, then this abelian threefold, Calabi-Yau threefold, is uniquely determined. So existence of positive entropy completely determined original manifold with fiber space structure. This is, I'm a bit surprised when I found this. So I'd like to discuss about this theorem today. And for Calabi-Yau threefold, if we have fibration over curve, then because this is simply connected, so base curve is necessarily a projective line, and general fiber is by adjunction either K3 surface or abelian surface. And for today, main part is abelian fibered case, but if we consider K3 fibered case, then this theorem does not hold. So there are many such fibered Calabi-Yau threefold. This I also discuss. And in this talk, important part is, of course, existence of some kind of automorphism with certain complexity. But mainstream says that if we consider a K3 fibered Calabi-Yau threefold, then never existence of positive entropy automorphism never identifies the fiber spaces. So there are some crucial difference between abelian fibered Calabi-Yau and K3 fibered Calabi-Yau. And one big difference is if we intersect for general fiber with second chunk class of Calabi-Yau is a very important fundamental quantity. But then, because just by using this exact sequence, we find that K3 fibered case, second chunk class intersect general fiber is just second chunk class of K3 surface, which is 24 and positive. But for abelian surface case, second chunk class of abelian surface, this is Euler number, logical Euler number, which is 0. So difference between these two, one difference is that vanishing second chunk class or non-vanishing. So in this main theorem, also second chunk class play some important role. And I'd like to explain positivity of existence of automorphism of positive entropy and second chunk class consideration gives this kind of identification. And plan of my talk today is first, I'd like to briefly recall the notion of entropy or more defined quantity, dynamical degree. And then this is some family of abelian surface or some family of K3 surfaces. But for surface itself, there are many cases where that surface has automorphism of positive entropy. This I briefly recall in second section. And third section, I'd like to consider a family of these surfaces and state main result. So what X is. And then, as I already indicate, second chunk class is important role together with these automorphisms. So I briefly recall my old result with Sakurai about Calabi-Yau threefold with fiber space, which contract C2. And finally, I'd like to give outline of proof of main theorem, how one can identify this kind of things. This is a plan of my talk. And first, I'd like to briefly recall what is entropy or dynamical degrees. This is after Gromov-Yongbin and Denis-Shibony. And if you are not so familiar with this notion, then please refer, and all paper I cite here are mostly published, but for ease to find, I'd like to indicate archive numbers. So if you are interested, please look at this. And let us start the notion of dynamical degree and entropy. So let X be a smooth projective variety of dimension D, and consider a dominant rational map, self-map from X to X. And algebraic dynamics or complex dynamics are interested in the iteration of these maps and how complicated this map. And one one most basic quantity to measure how complicated this iteration is the following quantity called piece dynamical degree of F, which is by definition, if choose one ample class on X, then we can take intersection of general one, then we get codimension P planes, then we take resolution of this indeterminacy by a smooth birational morphisms. Then we can just pull back of this general codimension P plane and then push forward it to source X and then intersect with complementary dimensional planes. And we consider exponential growth of this intersection number. And actually, the limit exists, and this number is called piece dynamical degree. And this is not entirely trivial, but one can also interpret this number as a operator node of this iteration map on the codimension P cycles modulo numerical equivalence. This is a free abelian group of finite rank. And this number is actually well defined, does not depend on the choice of H, and also does not depend on the norm and so on. And more importantly, in birational geometry, this number is birational invariant. This is proved by Dini and Shiboni. And more generally, if you have dominant rational map, equivariant dominant rational map of generically finite rational map, then dynamical degree does not change. This is also non-trivial but proved. And why this number is so important and considered as measure of complexity. This is going back to Gromov-Yonvin's first observation. And so we assume this is not just dominant rational map, but actually assume this is morphism. Then X is, of course, compact metric space. So we can define topological entropy of this self-map, which is originally defined as a measure how fast to general orbit spread out. This is just using metric, and one can consider this kind of this topological entropy for all compact metric space and its self-map. And Gromov-Yonvin's fundamental theorem says that when we consider smooth projective variety or more generally compact Kähler manifold, in that case, this space is PP class. Then topological entropy is computed as the maximum of all piece dynamical degree, but taking log. So this number certainly measures complexity of iteration of F or F. And one very good part, if we consider morphism, then this iteration, for example, this null, because this is morphism, then iteration and taking action on the cohomology is the same as first take iteration and first take action cohomology and iteration. So this part is just norm growth of F star. Then by each Jordan canonical form consideration, this is nothing but the spectral radius of the original F action on the codimension P cycles. And moreover, by Hodge index theorem, we have this concavity property of dynamical degree. So this number is really positive, which means which can be considered as F is complicated. Very in the most closely say that this is complicated if and only if first dynamical degree is greater than 1. And in that case, of course, this is spectral radius, or even for this order of F is certainly infinite order. So the automorphism considered must be always infinite order. And the first problem can be interpreted as interesting pair means first dynamical degree is really greater than 1 for automorphism case or birational automorphism case, or more generally endomorphism case. Choice depends on the interest of for each programs. And today, focus on automorphism case. This is a notion of dynamical degree. And for surface case, what one can say, if before surface, if X is a smooth projective curve, and if F is automorphism, then there are no smooth projective curve with first dynamical degree greater than 1. So if we concentrate the automorphism case, then curve is not so interesting in these programs. And first interesting case is projective surface case. And this case, there are two first breakthrough, both are around this century. First result is due to Cantor, which says that if X is a smooth projective surface, and assume there is automorphism of X with positive entropy, first dynamical degree greater than 1, then surface X necessarily birational to one of the following three familiar surface class: rational surface, or K3 surface, or end-case surface, or abelian surface. So K3 fibered case or abelian fibered case also some expectation to have positive entropy automorphisms. And and this is just a restriction, and I'd like to emphasize that even if X is K3 surface, some K3 surface never has this kind of automorphism. So this is just a restriction. And another interesting observation due to McMullen, this is also almost same time. If F is automorphism of first dynamical degree greater than 1, then first dynamical degree is some interesting, always become some interesting number called Salem numbers. Or more precisely, if we consider the action of automorphism on the Néron-Severi group, then this characteristic polynomial always factors as one Salem polynomial, and other part is all cyclotomic polynomials. And here, Salem number is real algebraic integer such that it is strictly greater than 1, and Galois conjugate of alpha is alpha and its inverse, and possibly other necessary imaginary numbers which is on the unit circles. So then this appears conjugate because this is defined over Z. So Salem number is Salem polynomial, which is minimal polynomial of Salem number, is necessarily even degree. And today, I don't need to enter some number theoretic aspect of these Salem numbers, but there are several interesting observations after these two theorems appear. So if you are interested, please take a look these papers and references therein. For example, first, Blanc and Cantor also considers a case where P2, then automorphism for P2, birational automorphism is not necessarily regularizable. So there are some other interesting phenomena appears. And another thing is what is the difference between Salem number and 1? And so smallest Salem number for each class of surface of some interest, especially Macmillan considers this kind of problem. And if you are interested in this kind of problem, maybe this paper is a last result for. So there are many information about the spectral gaps and so on from this paper. And probably more interesting, exciting recent result is Bell, Dira, and Johnson. They find some endomorphism, necessary rational endomorphism of P2 of degree greater than 1, whose first dynamical degree is transcendental numbers. So this kind of things are some interest, but today we don't need it. So this is some restriction, but actually there are a lot of cases where this class of surface has positive entropy automorphisms, which is important in my talk. So I recall some of them.
TJ, may I ask a question about the previous step? So basically, if you have a rational endomorphism, then we don't know any restrictions for the dynamical degree, right?
Please.
The dynamical degree of an automorphism is a Salem number. The dynamical degree of a birational automorphism is like something. Salem number was some other number.
Salem number or Pisot number.
I understand. And so for rational endomorphisms, you may have a transcendental.
Yes, and what kind of transcendental number appears is very interesting questions. And let us return back. They give one series of examples, but that is not all, I guess. So what kind of number really appeared is quite interesting, especially transcendental numbers.
And suppose that you have an endomorphism, which is a regular endomorphism. Does this give
then it is algebraic number?
Still algebraic, right?
Yes.
Thank you.
And today, this is not today's main topics, but if you consider all varieties and all dynamical degrees, then it is also known that dynamical degree number as realized as dynamical degree is only countable. So what kind of transcendental number is quite mysterious? May I continue?
Yes, thank you very much. Thank you.
Please ask a question if something you'd like to ask. And so first, I consider abelian surface case. Then this is quite simple examples, but in my talk, this is crucial. So I explain this. So let us take product, self-product abelian surface of elliptic curves. Then we have obvious automorphisms that point PQ, first coordinate goes to P plus Q, and the second coordinate is just Q, and also opposite one. Then this is clearly automorphisms. But in this case, if we consider characteristic polynomials on first cohomology group, then this looks like this because of this matrix form. And by using this, and second cohomology is just a wedge product of this, then dynamical degree of these two trivial maps are still 1. So this is not so interesting in our view. But if you composite 2, then matrix becomes this just multiplication. And in that case, we can easily compute characteristic polynomial, and from this dynamical degree become square of the maximal eigenvalue of this one. And this is certainly positive. So this is one example. And in this case, Picard number of T is either 3 or 4 and relatively big. And if Picard number is 1, then there are no positive entropy automorphisms because this is spectral radius on Néron-Severi groups, which must be 1. But for example, one non-trivial case is abelian surface with Picard number 2. In such a case, if you Néron-Severi lattice must be even lattice of signature 1, 1, but any such lattice can be realized as Néron-Severi group of abelian surface. This is by surjectivity of period map, similar flavor as case-free surface. In such a case, because and so especially there is many cases where two boundary of ample cone is irrational. In such a case, we can always find automorphisms of positive entropy. This is we can prove this in several ways, but for one way is cone conjecture holds to boundary, but two boundary are irrational, so automorphism must be after, if necessary, after taking square, these we have these two boundary rays, but at least one boundary ray, it must be eigenvalue must be greater than 1. Otherwise, no action here. So abelian surface, there are already a lot of examples which has positive entropy, and positivity of entropy never identify a surface itself. So then how about the case-free surface case? Another case-free surface case, the one typical way to construct K3 surface is to take anti-canonical member of Fanos threefold. One typical case is like this. In that case, we can find three involutions, which is covering involution of S goes to second two factors of P1 times P1, or first and third factor, or first two factors. So this is all degree two coverings. So we have covering involution, but this is for K3 surface. So birational automorphism is same as automorphisms. And by easy computation, each involution is entropy 0, but if you compose all, then we get positive entropy automorphisms, purely automorphisms. On the other hand, if we make this construction higher, then situation is drastically changed. In that case, automorphism is just identity, but all these kind of involution is really birational involutions, and birational automorphism is quite rich, but automorphism is empty in some sense. So this is a difference, and the higher dimensional example, some indication of higher dimensional examples of automorphisms. And another example is just take Kumma surface of the abelian surface I described in example 1 or 2. Then this automorphism naturally descends to automorphism of Kumma K3 surface, and in that case, dynamical degree is also greater than 1. And slightly different example is coming from Professor Nikulin and Alcock Dolgachev, and some part myself and Sun Yu studied. So considering two elementary K3 surface, this is by definition K3 surface with certain involution, which is act on Néron-Severi group identity, but for two-form minus identity. There are a lot of such surfaces and intensively studied by Professor Nikulin. And among them, there are cases where fixed locus is just become a union of P1s. And in such a case, from the first condition and Torelli theorem, all automorphism commute with this involution. But in addition, under this assumption, we see that this surface S always has automorphism of positive entropy. Most cases, we can prove this by using two different model value, different elliptic fibrations, which is positive model value rank, and then composition, some composition become positive entropy. This is some similarity with first examples of abelians. This is model bay to the second factor, and this is also model bay to the first factor. And composition certainly become positive entropy. This kind of argument, most cases we can prove this. Anyway, and such a surface, this number L is known to be 1 to 10, and number 8 has 2 families, so totally 11 families. And so there are a lot of such K3 surfaces. This I use later, so please keep in mind. And quite recently, Professor Sun Yu classified all Néron-Severi, that is of K3 surface of Picard number greater than or 3, which never has positive entropy automorphism. such lattice is only this number. So most cases, K3 surface has automorphism of positive entropy in some sense. Then how about the fibered Calabi-Yau case? So first, let us consider the case where X is a smooth member of anti-canonical members of Fano manifold of dimension greater than or equal to 4. Then X becomes Calabi-Yau default in the strict sense, but unfortunately, in this case, automorphism is always finite. This is based on the Collar's observation that under this dimension assumption, Néron-Severi group by Lefschetz, this is isomorphisms under this assumption, but more strongly, Nef-Kohn also preserved. And this is finite rational polyhedral cone. So this again, rational finite polyhedral cone. From this, we can conclude this. And also, in such examples, if we have fibration from V to P1 and taking anti-canonical member and induced fibration, but then fiber never become abelian variety. So this construction does not work. But if we allow X has singularities and take resolution, then we have, in some cases, we have abelian fibered Calabi-Yau. But for Voltier's case, but but if we just restrict to smooth member, then this construction does not help to construct examples. Next, considering Voltier boson type Calabi-Yau threefold, which is made from two elementary K3 surface and product of elliptic curve. Then we have involution of this form. Then action on the three form is trivial. So this is just Gorenstein quotient. So we have always take Crepant resolutions. In this case, just blow up of this singular point, which is A1 singularity along fixed P1s, image of fixed P1s. Then we have this fibration, which is K3 fiber, the Calabi-Yau. But because of the commutativity of automorphism with involution, this comes from two elementary. So we can reduce this automorphism to automorphism of X. Then this automorphism, fibered automorphism, which is over P1. But then, because of the generically finiteness, this dynamical degree is the same as this one, and this is finally same as original one, which is positive. So, in this way, we can find examples of K3 fibered Calabi-Yau threefold with positive entropy in the sense of automorphism in the sense of fibered varieties. And actually, in this case, topological entropy can, Euler number can be computed from the number of fixed P1. And if L is different, then X is not deformation equivalent to each other. So we have many examples of K3 fibered Calabi-Yau threefold, which has relative automorphisms of positive entropy. Then how about abelian fibered threefold? And one typical construction of abelian fiber, the Calabi-Yau threefold is chains construction. So let us consider relatively minimum rational elliptic surface with sections. And we choose two such one. And critical locus is intersection of critical locus empty, we assume. Then fiber product over same base P1 is smooth threefold, and it is easy to show that this is a trivial canonical bundle and less trivial part, but we can show that X fundamental group of X is also trivial. This is, for example, this paper clearly written down this in higher dimensional generalization together with. Then X is smooth Calabi-Yau threefold, and fiber is product of general fibers. So this is product type of abelian surface. And essentially, model value action give rise to automorphism of X. And one special case is this elliptic rational elliptic surface is isotrivial case, and also general fibers are same elliptic curve. In such a case, if the general fiber of this abelian fiber, the Calabi-Yau threefold, is just the product elliptic surface. So for each general fiber, we can find automorphisms of positive entropy as explained in example 1. And one thing is then one can make this fiber-wise automorphism together to get birational automorphism of X over P1 or not. And this looks true, but actually, if we can get this kind of birational automorphisms, then because of the fiber, there are no isolated rational curves. So this must be automorphisms and entropy must be positive. But as our main result says that this is not the case. So some delicate things happens. And final example is Calabi-Yau type. This is also studied Calabi, but only affine case, and Yau considered this in compact case, which is by definition, let us consider elliptic curve with period third root of unity. And then product threefold, self-product of threefold, and divided out by obvious multiplication by omega, omega, omega. Then this is Gorenstein. So for the same reason, we can get the Crepant resolution. In this case, just blow up 27 singular point of this type. Then this X3 become Calabi-Yau threefold, and famous Calabi-Yau threefold, as this is certainly rigid one. And in this Calabi-Yau threefold, the third projection is abelian fibration, whose fiber is just the product of two elliptic curve of this. Then we consider this automorphism of this product threefold. This part is as first example, positive entropy one. Then this is clearly commutator of this action, and this Crepant resolution, and also preserve this 27 singular point. So by the universality of blow-up, this gives rise to automorphisms, purely automorphisms, and last coordinate, this is identity. So this is automorphism as fiber space, and entropy become as first example, this is greater than 1. So this is one example of abelian fibered Calabi-Yau threefold of positive entropy. And my main theorem, actual main theorem is that if phi is an abelian fibered Calabi-Yau threefold, and if this has automorphism of positive entropy, then this abelian fibered Calabi-Yau is necessarily isomorphic to these examples. This is the main theorem today I'd like to discuss. And let us return back to these examples. In these examples, because either one of two fibers are just elliptic curve, so topological Euler number is 0. But this Calabi-Yau topological Euler number is 72. So this is not isomorphic. So we cannot gather automorphism in example 8 together to get the automorphism of fibered Calabi-Yau threefold. This is, I'm still some, I did not, actually this is as a consequence of this theorem, but I cannot really find a direct reason why that automorphism cannot be gathered together. So if you are interested, please let me know.
Keisha,
yes.
I understand that uniqueness theorem is complicated, and but anyway, you can produce such examples up to dimension 6, I guess, right? So you produce an example of a Calabi-Yau threefold, but you can also produce a fourfold and a sixfold in the same way, right?
This this Calabi-Yau?
Yeah, you can also produce a Calabi-Yau variety of dimension 6 in the same way, right?
Dimension 6 in the same way. Yes.
Just changing this omega by minus omega. Will it work?
This I did not consider yet. But higher dimensional case may be also interesting, but I'm not so sure the result is true or not, because my proof crucially uses x is threefold, as I explained from now.
Yeah.
So, and the rest, I'd like to give some outline of how to get this kind of result. I'd like to explain. And in order to get this result, I need one result from my old result with my student Sakurai. So I'd like to first explain C2 contraction, Calabi-Yau threefold with C2 contraction. So let X be a Calabi-Yau threefold, and considering fiber space over normal projective base with connected fiber, we call this is C2 contraction if pullback of ample class of W with C2 is 0. So this is then because this vibration is then given by some multiple of this, so C2 becomes C2 class of C2 is contracted. So I call this C2 contraction. And this is the same as that this is 0. And among C2 contraction, maybe this I don't really need. Among C2 contraction, we can also consider maximal one. So we call this maximal C2 contraction. Then this is a nice factorial property. And here I just emphasize that C2 is positive on ample cone, so that C2 is non-negative of NEF cone. This is a very deep result by Miyaoka and Yau. And one crucial ingredient for our proof is that C2 contracted Calabi-Yau is surprisingly very few in some sense. So let this X be a Calabi-Yau threefold. And if we have C2 contraction, birational C2 contraction, so over three-dimensional basis, then this contraction is only two. First one is Calabi-Mobile type, explained example 9, and one more example which comes from Klein chaotic curves and its Jacobian. And here, because essentially because automorphisms, and if, for example, X7 has abelian fibrations, then this is three-dimensional. Essentially, only two cases and both are three-dimensional. So this is maximal one. So that fibration factors through this, then we can lift to the fibration to A7 by taking Stein factorization. But essentially because there are no abelian surface, nor elliptic curve with order 7 automorphisms, so this has no abelian fibrations. And also PID property and factoring through this part, then all abelian fibration on X3, this is isomorphic to the one I give in example 9. So this is one ingredient. And also we can coarsely classify of C2 contraction to over two-dimensional basis. Then this is essentially the quotient of K3 surface times elliptic curve divided out by certain groups. So if you are interested in more precise description, please refer these papers. So this is structure of C2 contractions. And if this kind of picture will be given for higher dimensional cases, then we can get some result in higher dimension. But Dr. Gache proves that this is almost impossible. So now in the rest, I'd like to explain how to prove the main theorem, how to figure out one Calabi-Yau threefold from existence of positive entropies. So first of all, I considered fibered automorphisms, but this has always three singular fibers by Fibek Tsuo. This is general result. So by replacing G by power, automorphism we consider is may assume automorphism over P1. So identity on P1. And for we are now assuming this automorphism is dynamical degree strictly greater than 1. So we can find some NEF class such that it is eigenvalue of this one. 1 is dropped, but this is so-called Perron-Frobenius theorem applied for these pairs. So essential point is that this is preserved by any automorphism. So one can find spectral radius as eigenvector of spectral radius on this cone. This is a linear algebra result. And we put A is general fiber. Then first claim is that this divisor, we found one NEF real divisor, which corresponds to this spectral radius. But this actually non-trivial if we restrict general fibers. And by using this fact, and if this is true, then this number become also induced action of G on A. So this must be Salem number by Macmillan's theorems. And this part is not so difficult. Just if we assume this restriction is 0, then Hodge index type theorem says that this divisor class must be proportional to fiber class, but the eigenvalue is different, so never proportional. In this way, we can show that this is Salem number and this is non-zero. Then Salem number is, as I explained, if eigenvalue alpha appears, then its inverse appears. So if we consider inverse automorphisms, then this dynamical degree must be also positive because at least one positive eigenvalue this has. Then for the same argument applied for this, we can find another real NEF class, which is eigenvector of G inverse. So translated into the term of G, we have this kind of 3 divisors. Then all of these are NEF and linearly independent because different eigenvalues. And the second claim is that this intersection number is positive. This is similar way as before. And also, most important part is that then some linear combination of G's is NEF and big R divisor. And because I'll explain later, these 3 intersect with the class of C2 are all 0. So linear combination of these divisors become intersection with C2 also 0. And actually, if one can find really integral NEF big divisor of this one, then because of the some multiple of E gives contraction, birational contraction, and also intersection with C2 is 0. So this is C2 contraction, birational C2 contraction, and original X has abelian fibration. So as I said, this becomes this one. So finally, we want to consider this one. And most crucial part is this equality. So this is because C2 is invariant under group action. So if eigenvalue is not 1, then intersection with C2 is always 0. So C2 plays looks very important role in studying Calabi-Yau threefold and positive entropy automorphisms. And after that, we can easily to show that this class is actually nef big R divisor. But again, because K is trivial, so once we can find nef big divisor, then we can find rational nef big divisors. But this C2 is also rationally defined. So we can preserve intersection with C2 is 0 to change this R nef big divisor to rational nef big divisor. So in this way, we can prove the theorem. I'm sorry, first last part, but here most important ingredient is Kohn theorem and interpretation of Kohn theorem for K-trivial case that ample cone, nef cone is locally rational polyhedral cone in the big cone. So using this, we can approximate this as desired nef big divisor with C20. This is outline proof. And I just finish in 1 minute. First observation, first motivation of this main theorem is to consider finiteness problem of real forms of abelian fibered threefold. And actually, I get this if we replace by some birational models. But actually, this original observation comes from my recent joint work with 5 authors that Kohn conjecture implies finiteness of real forms. So, Calabi-Yau threefold case, real form must be finite. So, I want to try to see some special case. And if C2 is really positive on nef cone, then we can also show that finiteness. So this is the first case to consider. And during this consideration, I found that theorem. And another question is, I finished by 2 questions. First question is, X is not the exception. Automorphism looks virtually abelian group of finite rank. Virtually abelian means finite index subgroup is abelian group. And I wonder if this is really true or not. And second question is K35 Calabi-Yau case with positive entropy automorphisms. In that case, again, we can find 2 real nef big class which intersect with C2 is 0. So this case looks some similarity to the case of C2 contraction over a surface. And my question is how this case close to Calabi-Yau threefold with that C2 contraction to a surface case. And actually, Voltaire-Bazin example is one such examples satisfy this. And this is all what I'd like to talk today. Thank you very much for your attention.
Thank you.
Thank you.
Any questions?
I have a question, maybe not so, maybe stupid one. Can you expect something similar for Calabi-Yau which with elliptic fibration? Instead fibration on abelian surface, if you have Calabi-Yau having elliptic fibration over surface.
I see. In that case, if we consider automorphisms over the base. So
But
base
you
is
have no dynamical degree, right?
If over the base, then it is always entropy zero. Zero. Because fiber is elliptic curve and no positive entropy. So in that case, problem is action on the base space. Action on the base space. And if we really allow action on the base space, then the example, sorry, where? Example of this gives, so take vibration to first part, then this gives example of positive entropy. But in that case, positive part come from base. So if we only consider the automorphisms over base, then there are no such cases. Is this your question?
Okay, thank you.
And may I ask a kind of dual question?
Yes.
So suppose that you are interested not in threefolds, but in higher dimensional Calabi-Yaus, but
yes.
fibered over P1 once again.
Fibered over P1, yes.
Fourfold or something of higher dimension, fibered to abelian fibered over P1. What would be your expectation about the analog of your theorem in this case?
This case.
In the beginning of your talk, you explained an example when raising the dimension resulted into a finite automorphism group.
Yes.
Are you going to have something similar here? So basically, should
okay.
There will be fewer examples.
In that case, if I try to similar argument, and then first of all, this part is not really true, because at least we need some argument.
So we don't know how the dynamical degree of a fiber may look like, so we get stuck.
Yeah.
In the middle.
And even if this is not Salem number, but in some way, if we can find inverse is again some eigenvalue, eigenvector, which is again nef. And in that case, now I'm not so sure how C2 play roles. And higher dimensional case, maybe if we argue just follow faithfully this, then C3 intersection with C3 is more role. For example, 4-dimensional case. But in that case, C3, I'm not so sure how C3 behaves for Calabi-Yau fourfold or like this. So Cn-1 chunkless Cn-2, Cn-1 looks important, but one threefold advantage is C2 is in some sense understandable, and this is one crucial part. Can I?
Yeah, and maybe a very informal version of the same question. So you're explaining that the uniqueness theorem cannot be proved in the same way as for threefolds. But is there any reason to expect that So do you expect that, say, for Calabi-Yau 10 folds, many folds of dimension 10, do you expect that there should exist such examples with positive entropy, fiber-wise entropy, or you rather believe that should not exist?
First of all, I did not mention very precisely, but construction of automorphism of positive entropy for Calabi-Yau n-fold is quite difficult.
Yeah, and I think that at least your construction is I cannot imagine how your construction can be generalized into dimension higher than 6.
And in that case, already in my opinion, already very interesting to construct non-trivial examples of Calabi-Yau manifold of positive entropy in higher dimension.
But we don't have any approach, right?
Yes, this I have no particular insight perspective. This is an interesting question. Actually, original question of Professor Dini and Shiboni is coming from the difficulty to construct non-trivial automorphism of positive entropy for dimension greater than or equal to 3. And my talk today is say something about in dimension 3, some part can be doable.
Thank you. Any more questions?
I also have a question. I want to ask, is it true that in your example of this abelian fibered Calabi-Yau threefold with positive entropy automorphism, are there some singular fibers or not?
Singular fiber, I can, let's see. This case, singular fiber is there are three. This case, there are 3 singular fibers, and each singular fiber is just blow up of quotient of abelian surface product of E omega times E omega divided out by omega omega, and this has 9 singular point of type this one, and then because blow up of this point, so one main component is just the minimal resolution of the quotient surface, and which is rational surface, and plus 9P2 appeared as blow up.
Yeah,
I'm sorry.
Thank you very much. Yeah.
I can write down picture. I can write down. Then I can easily write down. But can you understand?
Yeah. I see. Thank you.
So and one more thing is that we can make several flops of X in fibers, but then automorphism never become automorphisms, just birational automorphisms.
Yeah, I see.
Because
Thank you.
we can show that they are not isomorphic because uniqueness of this contraction.
So, any more questions? If no, let's thank KJ again for a very interesting talk.
Thank you very much for your attention. And
Thank you.
So, slide maybe.
Can you say it again?
How can I put slide?
Yeah. So if you can send me the slides by email or by Dropbox or to Yuri, maybe it will be totally great.